Hello, everybody. I have been quite sick lately and haven't been able to make another video. But I wanted to finish up on the repair videos for this signal generator. And kind of wanted to show you all what was wrong. And that'll be the final video in this series. So, if you have any questions or any of my comments on here, when I refer back to the other videos, just take a look at the repair videos from the very beginning, and it'll kind of give you an idea of the evolution of fixing this thing. So anyway, without further ado, I'll get to it pretty quick. It's kind of an interesting problem that was present here. This is the schematic of the PLL divide by N timing circuits. And just to go over it real quick, you basically have some shift registers here. This is your, let's see, this is your clock line, and this is the data line. The data is clocked into these shift registers via this clock and then held on this data bus and distributed through the rest of this circuit. Now, if you refer back to the previous repair videos, basically what the failure mode for this device is that it was not centering properly per 100 hertz divisions. In other words, if you moved the frequency 100 hertz, it basically would move about 6 megahertz. And when I put it on the spectrum analyzer, and again, I refer you all to take a look at the previous videos, you'll see that the PLL does eventually lock, but it takes a long time to lock, and you could see it slowly go, above the frequency that it's set at. And what I mean by set at, it does not lock on the proper frequency, but it does lock. And that frequency is approximately about 6.6 megahertz, I think, too high. Please refer back to the previous videos because I really don't remember. But the point is that it does eventually lock, but it takes a lot of time to lock. And I originally, when I was diagnosing this, I had made the comment that I think what was happening is that the high slew rate in the phase detector, which is not this circuit, it basically, I think, is schematic number 11, if you refer to the service manual, that was not being activated. That essentially what the system thought, or that what the circuitry thought, is that it really was only moving 100 hertz. But in actuality, the PLL was moving 6 megahertz. And that's why it was taking so long to obtain a lock. And the way it works is that you have one counter here, which is basically a divide by 16 counter, and it's programmable. It doesn't always divide by 16. This is an ECL counter. Goes through these various stages to a logic level changer. This here changes the logic level from ECL to TTL. Then it goes to a second counter. Again, divide by 16 generally, and I'll get into that in a second. Then it goes to a third counter, which is this U20, if I'm not mistaken. Yes, U20. Now, whenever the frequency is changed within the band of 25.6 kilohertz, only this gets written and this gets written. This is not changed. Anytime it's within a band of 25.6 kilohertz, this never changes. And that fact is used to strobe the high slew rate pin on the phase lock loop phase detector, which is located on schematic number 11. In other words, it uses this right strobe here, this line here, which goes to schematic number 11. This is the right strobe for this counter. Whenever this counter is written to, it basically strobes this pin. This pin is then taken off and goes to schematic number 11, and that is used for the high slew rate. So the point is that changing 100 hertz does not strobe this pin. But yet, if you look at the repair video, the earlier ones, it thinks it is only moving 100 hertz, but it's really moving 6 megahertz. So this pin is not getting strobe, and I confirmed that as well. That's why it takes so long to obtain a lock. And that's what led me to believe that something was wrong with this circuitry. Originally, I thought something was wrong with this, this level changer here. This basically, as I said prior, changes the ECL logic to TTL. Again, in the previous video, if you take a look, you'll see that under certain conditions, that basically it was losing, either it wasn't the proper ECL, the proper TTL levels were not being obtained. Now, I pulled that transistor. I do not have a curve tracer, and I checked it out, in the simplistic fashion, just basically doing diode checks, and it was okay. I also checked out the capacitors, and they were okay. I checked out the diode, and it looked okay, which, was pretty stupid, but I just figured I'd change it all anyway. The point is that did not fix the problem, and in a way, Alberto, and if you're watching Alberto, which is one of my viewers, me and Alberto go way back when I started doing repair videos on the TDS 540 oscilloscope. And he kind of made a suggestion which turned out to be somewhat correct. And his point is maybe it's out of frequency range. Maybe this thing is being clocked at a level that is too fast. And that's the reason why it's clipping the proper TTL level. Now, in way of looking, this buffer here, which is the input to the divide by N circuit, I checked, and that is between, 60 to 110 megahertz. I checked that, and it was fine. So I just noted what he had said, and this is what turns out to be the problem. And let me tell you how this works. Basically, this entire circuit counts to a certain level, and then it puts out a pulse here. This pulse will be 100 hertz, a 100 hertz pulse, and that is then compared to this time base, which is derived from this 1 megahertz signal here, which is a divided signal from the 10 megahertz. I think it's 10 megahertz, if I'm not mistaken. I'm almost positive. Oven-controlled oscillator source or a regular crystal source. Mine has the oven-controlled oscillator option. And that becomes the time-based reference. So, of course, I'm sure you all know how PLLs work. It compares the two in the phase comparer, and then you have a charge pump, and then you get a lock. The point is that every time this circuit counts, it does a total count, a terminal count, and that terminal count is 100 hertz. It should come to here, and there's a pulse that's sent here. Now, what is interesting is that once that terminal count is achieved, everything is reset. And from that point forward, except for the first count that this counter and this counter go through, this functions as a divide by 16, and this functions as a divide by 16. But it only does that after its first cycle. And let me explain that. I know you all probably know about, how binary counting works, thanks to George Boole, Boolean algebra. But the point is that we have a nibble here, which is technically 4 bits. Goes from 0 to F, and of course, counts upward. And I just did this real quickly to show everyone. You have 4 bits, which are input to this counter. Now, I'm not going to worry about this counter here because it basically does exactly the same thing, and this wasn't what was bad. It was in this circuitry here. So just to diverge a second, I'm going to explain how this works, and I don't have the spec sheet out for them, but I'm just going to explain this very quickly. These inputs are 4 bits, which are taken from these latches, or one of these latches. And when this thing counts to F, that's considered a terminal count. This is active low. This will go low on that when that occurs. It then goes through this OR gate here, which is a synthetic OR gate. It's basically formed by not a regular gate, but by traces which are basically connected together. And what will happen on the next clock when it goes through this latch, this will go low and then load back in what is on this data bus here. So in effect, what it does is that every time it reaches a terminal count of 1111, which is F, it will reload and reload what is on this data bus. Now, that's the way it's supposed to work according to that's the data sheet. But the way this circuit is designed is that it doesn't do that except one time, and that is on the initial count. And what happens is that after the initial count, this latch is reset, and this is held high. Now, as this line is held high, what it does is after the first count, when it's loaded, and it counts to this terminal figure, it basically just rolls over to 0, counts to F, rolls over to 0, counts to F, which in effect operates as a divide by 16 chip. It basically divides by 16 this signal here, which is right from this input buffer. And of course, then it moves forward from there. Now, what was happening is that this latch was bad. This little latch right here was bad. So it was not holding this line high until the terminal count was achieved throughout the entire circuit, which allowed this chip to essentially reload every time that a terminal count was reached. It reloaded the data on these lines back in, which means that it was not dividing by 16. It was dividing by a much lower number, which let a higher frequency through the circuit, which then caused the latch to be clipped because it was being driven. And this is where we're back to what Alberto's suggestion was, which was causing the clipping and was in turn creating the divide by N to be offset by the 6 megahertz. Now, I didn't test this line because it was hard to isolate because it was ORed, not through a gate, but through basically traces being connected together. I checked this line, which is your non-inverting line. This is your inverting line on the latch. And this thing was dead. There was no activity at all. The latch was, the chip was getting power. You know, I checked that it was grounded, and it was getting, I think 5 volts, on it. I forget. I guess ECL would be 5 volts, and positive ECL would be 5 volts. Yes. And I checked that it was getting all clock signals to it, which it was. No activity on this whatsoever. The point is, I bought a new chip, put it in, and this right here was bad. So the way that this very cleverly designed circuit works is that only on the first count, and that goes for this one as well too, does it actually even use the data that is latched in from the microprocessor to change the frequency. Only the first count of this. Then after that, it always divides by 16. What that first count does is it delays this divide by N pulse by an extremely small window, which then is phase compared to the time base and is what causes the PLL to offset and change its actual frequency. So this is a very unique repair, very interesting design. I did the other two previous videos showing that it does work. It does seem to be very well calibrated. And if you all have any other questions or anything else, I'll go through it with you. But I hope I've explained this somewhat clear. I know it's not perfect, but very interesting repair. And it's on the rack. It's on the bench now, and it seems to be fine. So anyway, I hope you all enjoyed this video. If you have any questions, please leave them. And this is going to be my next repair that I'm moving towards. This is the repair of a Hewlett-Packard quad DC power supply. I already think I know what's wrong with it. I ordered the chip that I think is bad. In fact, I think what is bad is right there. Anyway, the point is the next video, we'll be moving on to repair this thing. I will be hooking it up and showing you all what's wrong with it before I desolder everything and try to put it back together again. I just wanted to complete this, do a completion video for this signal generator here and show everyone, so if they have the same type of problem, it might help them. Anyway, I hope you all enjoyed it. Again, any questions or comments, please leave them in the video, and I hope you all find this informative. Thank you.